Hello, hello. Hold on, my headphones got tangled up here. Hold on. Can you guys hear me? Are you there? Hello, Adam. Well, I got some bad news if this is the only reason you come on YouTube. Hold on a second. Let me get some stuff fixed up here. There you go. Oh. All right. Hey, everybody. Welcome back. It's Monday, April 4th. Yes. To what? Hello, everybody. Hello, Madison, Kennedy, Maddie, Chloe, Lucy. Oh, my weekend was nice. Thank you for asking. Hunter, Sharon, hello, Sam, Rachel, Nikki, Marin. Oh, look, all the all-stars. Hello, everybody. Hello. All right, so this is the end of the third quarter. I had a nice weekend. I've been doing a lot of work around the house for reasons that will become apparent after we get through housekeeping today. So let's I hope you all got outside and kept your social distance. Hopefully I got everybody there in the chat. Sorry if I missed anybody there. There's Tanya. Hello. Abby. Hello, everybody. Hello. All right. So we got some big housekeeping news before we get to quantum numbers today. So let's jump right in here. Let's jump right in once I get to the right screen here. Bing. All right, so again, I think actually it said I was going to finalize the third quarter grades tomorrow. I think they're finalized now. I think they're good. I just went ahead and added the last video quiz bundle. Other stuff got pushed back to this week, which means it wasn't technically third quarter. So I added one more video quiz bundle. I gave all of you a 4 out of 1. I usually steal 3 points from the next quarter if you need them, and I just, it's a pandemic, so I just gave everybody a 4 out of 1. There's a bonus assignment, so everybody just got those 3 points, so congratulations. And if you were close enough, I did go ahead and steal your second semester late pass. So I think I've done everything I possibly could to get you up to it. So I think we're squared away there. Is the optional MC due tomorrow or when we get back? Whatever I updated it to. I think I updated the optional MC. I think I made it for tomorrow. Whatever it says on Pearson, I think, for the next optional MC. I will be changing the rest of those around to mandated MCs, I think, only because we're going to be short on points for the fourth quarter. But we'll talk more about that later. So, yes, Sam, that's a very good question. I did shift some assignment due dates around. Just check to see what I have on Pearson for that. Whatever Pearson says goes. And if that sounds weird, just let me know. So here's the biggest news is that originally the district, and I understand why, was really hesitant about setting up and allowing live video for instruction because, they didn't want us looking in your houses or you're looking in our houses. And so there were some litigious things they had to get through. It looks like, and you guys got this email too, tell me if you're wrong, it looks like that the school district is going to allow live video instruction. Which means that, and there are 3 clients that they have authorized, and that's Microsoft Teams, Google Meet, and Blackboard Collaborate. Notice that YouTube live stream is not one of those. So the bad news is that it looks like, and I feel bad for Adam here, but it looks like that these live streams are going to have to die. It looks like after spring break, it sounds like the intent is that we are going to be using one of those 3 platforms, and I totally get it. I think it's because no, here's why. Because again, if the whole reason I'm using this avatar here is because they didn't want live video, and if they're going to allow live video, then I think we're going to have to bring it in. Well, listen. I think we are going to shift to one of those things. I think so. I don't think we're going to be allowed to continue to do this. I don't think we're breaking any rules here, but it's not in the intent of what the district wants us to do. And the whole point of these avatars anyway was to do this kind of live conversation. And so I've been checking them out. I know, alumni, I know the frustrating part is that we're not supposed to record stuff, and I get that too, but that does eliminate people who can't watch it. And it also for anybody else who might need it. I know. I'll find out more on the in-service on Wednesday. So what we'll probably end up doing is shifting over to either I think probably Google Meet, which is very straightforward. We can actually look at each other then, which is kind of nice. So we'll still do it, but I think we're gonna have to focus on just the students I have, as opposed to anybody who wants to come. I might check out Blackboard Collaborate too. It's got a few more bells and whistles. I don't know if I need them, but I'm gonna look into those. But anyway, so yeah, I feel like the live streams are not with what the district wants us to be doing. And so it was the Wild West for 2 weeks, and we did what we had to do, and this was wonderful. I might still do live streams, maybe I'll answer questions and things like that. I don't know. We'll figure out if we can continue to do this. But for day-to-day instruction, I think the letter of the law and the intent is not to be doing these, I think. But I'll find out. So again, I apologize that breaks anybody's heart. But we will continue live instruction. And then if you're one of my students, you'll actually be able to see me. And then we can have a little bit more interaction, I think. Which, I mean, is the point. I mean, it's not. I'm not here to educate the world. We're right here to really focus on you guys and my students. So we'll see. But anyway, so again, I think one of the big things is they don't really want this being recorded. And so I feel like even though all we're recording is the live chat, I think that's not probably what they intend. So I'll find out. So we'll see what I shift to after spring break. I do apologize for anybody who's here besides current students, but we gotta prioritize what the district wants. And I get it. The whole point of this was, again, to kind of get us interacting in some way if we couldn't do live video, and that's where the avatar came in. So we'll see. Anyway, so that's where we are. I have the whole point is this weekend I've set up a home studio in my basement. So I actually have set up a nice little set here, which I'll have to show you at some point. So I think when I'm doing the live stream, it'll be a nice little place to actually videotape. And I've also set it up now that maybe it's easier for me to do some videos from home. So I would like to go back and start recreating all of my old content, starting with probably Modern Atomic Theory, because I like what we did. So there will be new content, hopefully. So, again, we just got to keep adapting and adjusting to the new situation. So I know. Maybe we can just have an alumni hangout, though. We have our Google Hangout. Anyway, so now that I've broken some hearts, though Adam, I will say, just as a shout out to Adam, PA Pokemon is back creating content again, so you can hang out with him, I guess. All right, so what we're going to do today is dig a little deeper into the idea of quantum numbers. Again, I think the videos were pretty self-explanatory. There were 3 videos that you could actually watch. I have 2 videos on the numbers and then 1 video on some practice. What we'll do today is go over some of the rules with 5 more years of experience under my belt teaching this stuff. So I think it's pretty good. And then tomorrow we'll go through some examples. And again, once we start doing maybe live video, maybe we could do a little bit more interaction than just the live chat, which is kind of minimal interaction, I think. So anyway, so what you see here are the 4 quantum numbers that you're going to have to deal with. All quantum numbers are a way of figuring out where electrons actually live in this complex quantum mechanical world. The take-home point is that you guys need to be able to give any electron an address, and you need to be able to look at addresses and say, no, that's not a legitimate place for electrons to live. From a global point of view, we start with a very broad address. In the video, I talk about what planet you live on, and then as you go down, these become more and more specific. They're not that bad. What you need to understand is these are the I guess ramifications of the models of Bohr and Schrodinger. Now remember, those were mathematical models. They were complex mathematical models, and so a lot of these weird numbers come from these wave mechanical models of Schrodinger and then the energy levels of Bohr. So if it sounds weird, it's because it's based on the math we didn't talk about. So don't freak out. Anyway, so let's just kind of march through these today. Again, if you have any questions in the chat, let me know as we go through this. We'll do, and again, I think we'll do one more live lesson tomorrow. I think I'm still allowed to do this for now, and then we'll shift. So the first quantum number, which again, sort of like you want to join the secret society of the quantum rangers, as I used to call them. And so the first one that you just stand at the door and say, "Can I join you?" And they're like, "No, but you can go clean our stable." And they're like, "Oh, okay." So you go clean the stable until they eventually invite you into their secret society. And the first quantum number, N, deals with Bohr's idea of these energy levels. These allowed distances from the nuclei. And we already talked about where all this stuff came from. And so this is a throwback to that. This was sort of a one-dimensional sort of address. What energy level are you on? Are you on level 1, 2, 3, etc.? Remember that these energy levels are farther and farther away from the nucleus. These are called energy levels. You will occasionally hear them called electron shells. These values, I guess, again, math people help me out. These would be considered positive integers. Yes, Adam, they are easy and fun. Yes, Adam has pointed out that quantum numbers are easy and fun. And they're just a weird, goofy little code, which will make you sound a little bit like a cult when you start using them. But they really aren't that bad. They're not that bad. The first one's pretty easy. There are no known atom has a ground state electron above the 7th energy level. And that's important to point out. Remember that electrons are either in their ground state, which means that they're not excited, so they're as close to the nucleus as they can be, or they're in an excited state. Excited electrons can live anywhere in the atom beyond the 7th energy level. Remember, we showed you as you get beyond, these energy levels get closer and closer together until essentially you get an infinite distance from the nucleus itself. But if we account for the known elements, we don't need anything beyond the 7th energy level. Now, again, if we discover one more new element, we'll be in the 8th energy level for ground state, but maybe that's your job, Get that Nobel Prize. Now, when electrons get excited, they do hop up to higher energy levels. I used to say they teleported. Apparently, that's wrong. They just transport up there very quickly, like in a couple nanoseconds. So they're going to jump up to higher energy levels, and then they're going to transition back down. When they transition back down, again, that's when they go off the bright line spectrums. So the first energy level is really critical to understanding bright line spectrums, and it's very easy. And so again, what is a legitimate address is stuff like 1, 2, 3, 4. Can it be 0? No. Can it be half numbers? No. Can it be negative numbers? No. So the first energy level is a piece of cake. All right. So that's an easy way to figure out electrons. Again, if there's any alumni out there, throw in your 2 cents too. And again, as I pointed out, when they release that energy, they drop back down to some lower energy level. Sometimes they give off visible light, and that's if they jump to the 2nd energy level, right? Anyway, so the rest of the quantum numbers all come from Schrodinger and his wave functions. And again, we didn't talk about the math. I don't think it's really important at this level. I think if you are accepting the fact that this math exists and it's something that you don't want to do, then, I don't want to deal with this. Do you want to deal with that? I don't want to deal with that. So we just have to kind of accept the fact that people smarter than us, maybe smarter than me, maybe not smarter than you, I'm sure you can handle this math, crunched the numbers and found these complex mathematical explanations where electrons live. And the rest of the quantum numbers all stagger off Schrodinger's equations. So again, are they weird? Yes. Do they have weird names and symbols? Yes, but all of these have some basis in his history, whether it's the color of lines in the spectrum or anything like that. So again, all of this can be explained if you want to. And so these last 3 quantum numbers will help define exactly where electrons are, and they get more and more specific. All right. Remember, orbitals are those, if you remember from last time, orbitals are really mathematical functions that describe where electrons can be in terms of probabilities. They're complex and they're weird, but if we cut them off at 90%, then we get these, satisfying looking shapes. And so really what these shapes are the probability patterns of finding electrons. And so notice they get more and more weird as you change the orbitals. And so that's an important thing to understand. Each one of these things can hold up to 2 electrons. And believe it or not, we can have a really very simple way of figuring out where electrons live in the complex quantum mechanical world. All right? So that's what we're going to run through today. We already did it in the video, but we'll do it again. Now, again, imagine, I'm trying to look at the bright side of this. When we go to something like Google Meet, right, you guys can be, jumping in and asking questions. It'd be a little difficult with 100 students, but only about 20 of you show up anyway. So it'll just be like a regular class for the kids that just want to show up. Invite your friends who aren't showing up. But again, we can have alumni wrap maybe sometime too. All right, so let's look at the second quantum number. This is a cursive L. Very hard to find fonts that have a nice cursive L. So anyway, that's what they use for cursive L. Now, this has a lot of other names. I always called it the second quantum number, but it goes by a lot of other names, not called the second quantum number, like the azimuthal, the angular, the orbital quantum number. It is what it is. So it's got a lot of different names. All right. Again, if you care, this is related to the magnitude of the angular momentum for you physics fans. I don't really know if I even care about that. Really what this is saying is based on the energy, what shape orbital does the electron live in? So I go back to this analogy of think of energy levels as sort of the street you live on. I always say, like, I'm going to write this dystopian teen fiction, that used to be popular, where you guys all live on this mountain and you can never get down to the center, to the nucleus of town. It's verboten. You're not allowed down there, but you live on either the first street, which is closest to the energy level, or the second or the third or the fourth, and then you can jump between streets. And on those streets, you start to get different shaped houses, and as the orbitals represent the shape of the house you live in. And so we're going to spend a lot of time on L. This requires the most time because it has the most information. But after that, we'll blitz through this pretty quickly. And so the second quantum number really tells you the type of house you live in, the energy of your house on that energy level. If you have the same street number, energy level, right? And if you live in the same shaped house, you're in what's called the same subshell. Okay? So we'll talk about what the subshells are. It's very important that you know these. And it's really cool. After spring break, I'll show you how the periodic table is actually built around this information. Everything we have is structured based on this quantum mechanical underpinnings, which is really cool. Now, again, we have these cascading codes, which are the fun part, as Adam would say, of the quantum numbers. And so the values for L can be anything from 0 to n-1, which sounds confusing, but if that just simply means if you are on the first energy level, then you can only have an L of 0, right? And if you are on the second energy level, you can have 2, either a 0 or a 1. Or if you're on the third energy level, you can have 3, 0, 1, or 2. And then if you're on the fourth or beyond, you can have 0, 1, 2, or 3. It's actually really pretty simple. It's just that the numbers sort of shift down 1. They start with 0. And again, this is all sort of based on the quantum mechanical math, which is why it's that code. Now, you can have orbitals beyond L equals 3, but those are only for electrons in excited states, and we don't have to worry about them at this level. Higher energy levels, so the farther you are away from the nucleus, you have access to different types of higher energy orbitals for the electrons to live in. And I'll show you this. We'll walk through this, okay? It's a little weird, but it's very, very cool. It's a very simple way to figure out where electrons live. And so the first example, the first energy level that electrons, on the first energy level, the first orbital you can live in is what's called an s orbital. All right, it's a spherical orbital. It is the lowest energy orbital, always available on any energy level. Every energy level has an S house. And an S house is code 0. So again, if you want to use the quantum number codes to talk to your friends, if you want, for some reason, to tell people the number 0, but you don't want to tell them the 0, you can say, hey, S. So there you go. You have a code, a very limited number code. And so if you have an S orbital, which is the lowest energy wave function for an electron to live in, we give it the code S. And that S has some kind of historical preference, I think based on the color of the lines in a bright line spectrum, I think. And that's why it's called S. But you can think of it as spherical. Super easy, okay? Again, every energy level has an S house, and it's always the lowest energy. All right? That's it. And that's really all you need to know about S. They have a very pleasing, simple shape. It can hold up to 2 electrons. So every orbital can be a house for 2 electrons. So on the first energy level, can you have an S? Yes. On the second, can you have an S? Yes. Third, yes. Fourth, yes. Every energy level can have an S. And so it gets this designation. For instance, the first one would be called 1S, right? It's the S on the first energy level. And the second energy level, we'll talk more about this later, would be another S that just overlaps it in space, right? So you have another S, and that would be the 2S, and it just overlaps it in 3D space. And again, you could have another S. The third, oops, that got a little sloppy, would be like a 3S, and they can just start to overlap each other, all right? So it gets a little weird, but that's pretty simple. On the second energy level, not only can you have that S, so we'll draw it over here, zip, zip. So you can have an S on the second energy level. So here's your second energy level. You can have an S, and then you can start having these p orbitals. And again, that's why you don't draw these, because look how weird this is starting to get. All right. So on the second energy level, you can have L equals 0 or L equals 1, right? 2 minus 1 is 1. It's a weird code, but you can get it. All right, these are known as p orbitals. And when p orbitals show up, and we'll talk more about this in the next quantum number, you can have 3 equivalent orbitals Okay, there's only one S that shows up, but when P's are allowed, boop, 3 houses appear. All right. And the P orbitals are always higher energy than the S. So the S is the lowest energy level. It's the closest to the end of the street. But if you walk a little farther and put in a little bit more effort, you can get to the P subdivision, as I call it. All right. And again, we'll talk a little bit more about where these come from later. But that's all. So on the first energy level, we can only have an S. On the second one, we can have S's and P's. And as you can guess, on the third energy level, we introduce the weirder D orbitals. Now, P you can remember sort of by the name P or peanut. D, I don't really have anything to go by. They kind of look like clover leaves, but not all of them. And again, these higher energy, more complex wave functions start to show up on the third energy level. And so there are even more places for electrons to live. All right. And so when you get to the third energy level, all of a sudden this whole new subdevelopment opens and they have all of these weird, funky shapes, all equivalent energy, but all higher energy than P's and D's. And it's weird, but it's okay. Don't worry about any of these designations. Don't worry about it. Okay. Just understand that when D's show up, they're higher energies than S, they're higher energies than P, and there are 5 of them that show up. So notice there are all these really satisfying patterns that show up in quantum numbers, right? N can be 1, 2, or 3, right? L's represent the different type of orbitals, and they open up. S's can be on 1, S's and P's on 2, S's, P's, and D's on 3, right? And there can be 1 S, 3 P's, 5 D's. And there are all these very simple cascading patterns, all right? And most of these cascading patterns will actually even kind of be simplified when we get to drawing next week, which is even easier. All right. Now, the last type of orbital we have to deal with is the fourth energy level. So on the fourth energy level, right, we have, and this goes for beyond this too, right? On the fourth and beyond, we have what are called F orbitals. All right, F orbitals are the highest energy. And then when they show up, again, 1, 3, 5, you get 7 of these like jelly bean, Ferris wheel, Stonehenge sort of wave functions. Notice that they're not connected because this is the 90% probability of finding electrons. So there are these spaces in between where there's less than 90%. That's why they don't have to be connected. There are orbitals beyond the F, but we don't deal with them in ground state electrons. It's for excited electrons. We don't have to worry about them. Okay? And so that's really it. We have to spend the most time on L because the orbitals are just so important, right? But just remember the pattern, right? On the first energy level, there's only enough space for S orbital, right? On the second energy level, we can have another S, and then we open up P's. On the third energy level, we can have enough room for S's. We still have room for the P's, and then we open up the D subdivision. And then finally, on the fourth and beyond, we have the S's, the P's, the D's, and then we open up these wild F orbitals of high energy. Okay? And that will handle, believe it or not, all of your ground state electrons. Okay? So that's N and L. That takes the most amount of time. All right? Now, what we're getting to is what was covered in the second video, and that's the idea of the magnetic quantum number. So as we pointed out, right, let me get these notes out here for you. I think that's all of them. Oh, there they are. We can have S's. There's only 1 S that shows up, but there's 3 P's when P's show up. There's 4 D's when D's show up. And there's 5 F's when F's show up. And so now we've separated these all out. Please understand, again, these are all going to overlap on top of each other in 3D space, which makes these almost impossible to draw, right? So imagine all of these axes all overlapping and we just dropping all these things on top of each other, which would actually be pretty cool. I should probably draw a picture of that just to show you how wild this gets. And so once we start having these equivalent houses where electrons can live, we have to say, hey, which house are we living in? All right, and that's where M sub L comes into play. M sub L is just a simple code of saying, okay, what's the house number, right? Now, again, house numbers in the real world tend to be positive integers, sometimes halves, but, we live at 1 Elm Street, 2 Elm Street, et cetera, et cetera. There are no zeros. There aren't any negative numbers, but there could be negative numbers. That's just the way we decided to do street numbers. I could imagine a different reality where we had Main Street, right? And all the houses north of Main Street had positive numbers, and all the houses south of Main Street had negative numbers. And that's a real quick way of you knowing whether your house was north of Main Street or south of Main Street. It doesn't mean that you live in like an antimatter house or anything like that. It's just a designation that makes sense. And so don't get freaked out if you end up getting a designation for your orbital that's a negative number. It is just an arbitrary number. They could have definitely just said 1, 1, 2, 3, 1, 2, 3, 4, 5. They just didn't. Because again, we have this fun cascading code, right? You know, to figure out which house you live in or which houses are available, you look at your L, right? If L equals 0, right, then the only value for M sub L is 0, right? If your L equals 1, right, then we have 3 values for M sub L, -1, 0, and 1, right? See how easy that is? And that's it. All this is just a very simple way of figuring out which orientation you live in. They're all the same energy, just which house is it? Okay, so look at the pattern, right? If L equals 2, then we can have -2, -1, 0, 1. I don't know why I'm drawing with a mouse. This is why it's so difficult. I should have been drawing with a pen. I don't know why I did that, right? And then look at this, ready? So this isn't going to look any neater, but I'll feel better about it. If this is 3, then, right, we could have -3, -2, -1, 0, 1, 2, 3, right? And that's where these possible values for M sub L come from. Super easy. Don't get freaked out. Don't worry about which M sub L is which shaped orbital. Who cares, right? At this level, it's irrelevant. All right. So once you see this, I think it's really kind of easy to see that, you know, we have to figure out A, what street do you live on? Okay, that's the energy level. B, what kind of house do you live in? Do you live in an S-shaped, P-shaped, D-shaped, or F-shaped, right? And then, okay, but which house do you live in? All right. I know that there's a subdivision of P's. Which P is it? There are D's. Which D do you live in? Which F do you live in? And all this is your address. This is your house number. Super easy. Okay. Obviously, if you're S, there's only one house, so they always have the same address. They'll be on a different energy level, right? I mean, again, you don't use up the number 32 because you're 32 Elm Street, right? You could have a 32 Pine Street and a 32 Willow Street, right? Willow, right? Does that mean for S, there is only one possible location for the 2 electrons? Yes, right? Yes. So there is going to be, there's going to be one S orbital on every energy level. But to kind of rephrase your question, there is only one orientation available because it's low energy. So yes, if you're in an S orbital on an energy level, there's only one house, which means only 2 electrons can be in an S orbital on any given energy level. Every energy level can have an S orbital, right? But there's only one house. All right, so to follow up on your question, that means for a P subshell, when they show up, right, not on the first energy level, but on the second energy level, there can be up to 6 electrons living in P orbitals, right? Each one of these houses can hold 2 electrons, right? So when you have a P subshell, right, up to 3 houses can be there with 6 electrons. Yeah, exactly right. Derek brings up a great point. The first street is a 1-house street. That's an excellent metaphor, but perfect, right? There is only one house on the first energy level, which would be a very interesting plot point in my dystopian teen fiction. Why is there only one house on that first street? And why can't we get down to the town center? My goal is to write a dystopian teen fiction using quantum mechanics and not tell anybody it's quantum mechanics, and then it becomes super popular, and at the end of the big reveal was, I just taught you quantum mechanics, and everybody's like, we hate you. That would be my giant, huge troll of the young teen fiction dystopian book market, would be to totally troll students into just teaching them quantum mechanics as they learn about the different streets. Yes, exactly right. So Derek was perfectly correct. It's a 1-house street. The second street then would be a 4-house street. You would have the S, and then you'd have the 3 Ps. The third energy level, sticking with Derek's excellent analogy metaphor, is you'd have a 1, 2, 3, 4, 5, 6, 7, 8, 9, 9-house street. And then etc. We could add more. Perfect. Great job. Perfect. All right. And this is how, if you follow that cascading rule set, if M sub L can be anything from L to -L, right? If we go all the way down here, if L is 3, then we can go everything from -3 to 3, which gives us 7 houses. It's weird, but it's really not that complex. All right, we're almost done. We're almost done. See that? Oh, thank you, Derek. Gold sticker for the day. Thank you, Alexandra. Great point. Adam, also great job. Thank you for saying quantum numbers are easy. You're making me feel good. All right, so the last spin number is M sub S. Okay, and this is a very, very simple idea. As I've kind of anecdotally pointed out, you can fit up to 2 electrons in an orbital, but electrons don't like each other because they have the same charge. And so what they do is they spin opposite ways. Now, it is not a true spin. It's not an electron, as I understand this, with a big caveat here, big caveat. Look, I'm gonna give you a frowny face. Big caveat. There, see that? See that emoting there? It's not an actual spin. Remember, we really shouldn't be looking at electrons as little balls with an E- on them. So by spin, what we're really talking about is like angular momentum. And again, there's lots of good videos. I actually really highly recommend this channel called Looking Glass Universe. She's this excellent postdoc in physics who did a lot of really great whiteboard animations to try to explain quantum mechanics. She's wonderful. I really like her channel a lot. She's actually recently started doing some live videos, and she does a video that I linked to about becoming a quantum physicist, and she does another video about COVID-19 and stuff. So she's a really fun, high-level resource. She doesn't talk down to the viewers. Really exciting stuff. But anyway, so spin is really a representation of electrons trying to get away from each other. It's a really simple idea, though. Inside the house, there's really 2 places you can live: spin up or spin down. And we just represent those 2 values as +1/2 or -1/2. And again, this all comes down to quantum mechanical math. So as long as an electron has one of those 2 values, it's a fine value for M sub S, right? As long as it's +1/2 or -1/2, that's legit. That's as simple as it is. Now, arbitrarily, the first electron is given a spin up designation, but it's not a big deal. I think it has something to do with slightly less energy or something like that. I feel like I looked it up once, but again, it's not really that big of a deal. And that's it. So those are the 4 quantum numbers. They start with something very broad. What energy level are you on in a specific atom, right? Not atom as in the chat, but atom as in the atom. And then what inside that energy level, what orbital are you in? What type of orbital? And then once I know what kind of orbital you're in, M sub L tells you which of those equivalent orbitals are you in. They're all L's. I mean, they're all P's, but which P? They're all D's, but which P? And then finally, inside that house, where do you live inside that house? All right. So hopefully that helps. Hopefully that's a nice overview of what I talked about in those other videos. Tomorrow, like I said, we'll do some practice problems together just to talk about how to figure this out. Oh, by the way, this ties into the Pauli exclusion principle. This guy is Wolfgang Pauli. Actually, I think a very gruff, sarcastic, sort of unlikable personality in the real world. He was very mean to people, I think. He didn't really suffer fools. He famously once said he was reading like a doctoral paper, and then he said, this isn't right. This isn't even wrong. Meaning it's like so bad that he had no idea what he was talking about. But anyway, Pauli exclusion principle states that, and this states, I guess it sounds pretty simple at this point, is that within an atom, no 2 electrons can share the same set of quantum numbers, right? So once we find these 4 designations, no 2 electrons in the same atom can share those 4 quantum numbers, which I guess sort of makes sense. So that's Wolfgang Pauli. Did other stuff too. Predicted the existence of neutrinos as sort of a Hail Mary to save the law of conservation of mass. And then it turned out he was right. And people discovered neutrinos. And that's a fascinating story in its own right. There's a really good documentary out there called The Ghost Particle that's probably still illegally pirated on YouTube. It's old now, but still very fascinating. Great scientific investigation story. Anyway, one final point I want to point out is that orbitals do overlap. Sometimes students don't realize this. And so again, we can have S's that overlap, and they all overlap around the center, right? And then notice this is a great drawing here. Again, here we have a 1s, a 2s, and then we have the 2p. And so notice how complex the 3D space gets. which is why we don't really draw these things overlapping anymore. But it's a really, really neat way to visualize this. I also want to point out that, again, when we talked about electrons not being able to fall into the nucleus, that was actually under the assumption that electrons were classical particles. They're not. They actually have these quantum mechanical probability functions. And so one of the things I've realized is that wave functions can actually overlap the nucleus. They all do, in fact. And so electrons can actually exist inside the nucleus. They just don't get trapped there. If they do, that can actually cause a type of radioactive decay. So that's kind of neat that you have to get out of this idea that electrons can't fall into the nucleus anymore. They actually can exist inside the nucleus based on wave functions, right? I mean, look at this wave function right here. It has to overlap the nucleus. They just don't get stuck in there. Which is pretty interesting. I guess they have to interact with the nucleus, and if they do, that could be a problem. But anyway, so keep that in mind. You have to let go of a lot of your prior assumptions of what atoms look like. Again, this is why we still use the planetary model, because it's our last visual model of the atom that has a nucleus and sort of like attritional electrons on the outside. All of these mathematical models are impossible to visualize. If you think you're visualizing one aspect of it, you're falling short on other aspects, right? Even these orbitals themselves is a mathematical compromise. So again, next time, we'll do some practice. Again, I want to point out that tomorrow's lesson will probably be, and I know this is probably going to break some people's hearts, but I think based on the intent of the district's new sort of ideas on remote learning, this is not one of the idealized ways of reaching out to students. A, because it has less interaction, and B, because I guess we are recording the live chat, and I even though I guess that falls outside their previews. So I think I still will try to find a way to reach out. I think I don't know if there'll be a big audience if it becomes non-semi-mandatory. But I have enjoyed these live streams, so I don't want to lose these technical chops. So again, we'll figure this out after spring break. This is you on spring break. No one is around. So we will, again, if you weren't here at the beginning, we will continue sort of live collaboration with my students, but it probably will no longer be on YouTube live stream just because they are trying to consolidate the ways we reach students and allowing live video, and I totally get that. So it'll just be my own students in probably Google Meet, I think I'm leaning towards right now. So listen, we all have to adjust. No, my current students shouldn't be sad. We'll actually get to see each other. It's just my prior students and any guests that I think will be brokenhearted. But I will then redouble my efforts to create new content. I'm going to go back and start redoing my higher content videos. So anyway, So we have a couple, and we can still do terrible improv. It just won't be for a worldwide audience anymore. So go ahead and let's throw in some requests here for the live improv. Draw a graveyard. Okay, I can do a graveyard. What else? A graveyard. I'll start the graveyard, and then a hacky sack. Why a hacky sack? You said you wanted to draw them all together to make your dreams come true. I think I can Al Capone, El Chapo, or Pop. No, I can't. Why do you want me to do those things? I can do. Graveyards are easy. That's one of the things I used to draw all the time when I was a kid. I told you I used to draw haunted houses. So we'll draw some gravestones here. With some leaning gravestones and stuff. It's easy to draw gravestones. See how easy this is? Look, here's a gravestone. We'll put an angel on top of this. There's an angel reaching out. Little Doctor Who reference here. Whoa, that looks more like a bat. Sorry about that. Little weeping angels there. Rest in peace. Live stream. Rest in peace. Oh. Alumni. Contact. And again, what else do we have? A hacky sack? Hacky sacks are easy. We can do a hacky sack. We have some sad people upstairs. The live stream's ending. There's a hacky sack. Yeah, don't blink. Exactly. And there's the natives are getting restless upstairs. There's a ghost for you up there. They're coming down. Hey guys, what's going on? You guys want to come down and say hi? Come on down. Come on over. You guys can say hi to my students since these live streams are out. Here we got one of my... you want to say hi? Come on. You guys want to say hi in the live stream? Who are you?
Luca.
Lucas says hi to everybody in the live stream. Hi. Who else is here? Hey, what's your name,
Jude.
buddy? Jude, you want to say hi?
Hi.
Hi. Jude says hi to everybody on the live stream. My wife's here. I don't know if she's going to say anything.
No.
Nope.
You just said something, Mom!
So, yeah. So, they say hi to you. They say hi. She's excited.
Do you have any more blue tape?
Somewhere. I'll find it for you, honey.
Come on.
So anyway, so this will be, I think, anyway, there you go. Yes, Lucy Simmons. So anyway, so we have at least one more live stream, and we'll do some practice tomorrow, and we'll figure it out. Like I said, we have to continually adjust and adapt to the new expectations of remote learning, and so I'm for it. I'm okay with that. So anyway, so listen, I've enjoyed our time together. I think that's it. So we'll figure something out. Email me your suggestions. Tell me some thoughts in the chat. We'll keep this going in some way. So anyway, we're getting ready for spring break. Woo! Quarantine spring break. All right, everybody. I'm excited. I am excited to show you my studio at some point. So I spent all weekend working on it. So email me with questions about third quarter's grades. Thanks for watching. Stay safe and have a great day.